Hello, and welcome back to the course on distributed systems. This is the first video out of 3 talking about time, clocks, and how to synchronize clocks, and how to use synchronized clocks in protocols. So the first point on the agenda is talking a little bit about the nature of physical time and clocks, just so we're on the same page there. And then in 2 follow-up videos, I'll talk about how to synchronize clocks and how to use them in so-called bound-based protocols. So let's just jump into talking about physical time. Talk a little bit about physical time and clocks. The first message is there is no physical time, there only is clocks. If we look at the definition of what time is, then we have a definition of a second, which says it's the duration of 9,192,631,770 periods of the radiation corresponding to the transition between 2 hyperfine levels of the ground state of the cesium-133 atom. I don't even know what that means. But what's important here is it's something to do with an atom. I mean, we're looking at an atom, and then it does something, and then whenever it does it, we count, and then when we count it to this big number, that was a second, right? So we took an atom and we turned it into a clock. So that's how time is defined via clocks. And then some of them are more precise than others, and we'll deal with that when we look at clock synchronization. It might look like a big number actually, but just for comparison, when I was doing these slides, the CPU clock speed of the fastest computer produced is actually a similar number. So I guess when I'm doing this video here next year, computers will have a clock that's faster than this shaking up there of that little atom. So we could redefine time to being that number of clock operations on the computer standing in some basement somewhere in Sønder, assuming that it's precise enough. As long as we have a definition that we can all agree on. Okay, so that's what time is. It's clocks. The way we then measure time is to its greatest precision is via atomic clocks, which it's a type of clocks that is using our definition very operationally. Okay, so it traps a cesium-133 atom, and then it looks at it. It transitions between these fine ground states, and it counts them, and then it just counts to that big number there. And then whenever it counted to that number here, it increments a register on the computer, and 1 second has passed. Actually, it does it more often because we want nanosecond precision probably on the computer, but that's what they're doing. You might imagine, these things, I mean, to get that kind of precision are rather expensive. So that's not the stuff that's sitting in your computer, unless you have a very expensive computer. They look like this. This is an example of an atomic clock. It's in Switzerland, because as we all know, the Swiss are the best at keeping time, so they do it for us. This one is called Fox 1, and it's so precise that it will drift about 1 second in 30 million years. So that's a very precise clock. So that's also maybe hence why we don't put these things inside our laptops. Then, just as a caveat, before I'm gonna define a global clock, let us just all remind ourselves that such a thing doesn't exist. There is no notion of global time. There's some common time that we can all kind of access. This is all Einstein's fault, of course, because he had to go and invent relativity theory, which have been causing all kinds of problems since he did that. But anyway, that just means that even if you have the most precise atomic clocks, and you have them 2 different places in the world, they will drift apart, not because there's something wrong with the clocks, but because there's something wrong with the world. I mean, the time just doesn't travel at the same speed in different places, in particular if you undergo different acceleration and gravity. However, for the purpose of this course here, assuming that our computations are going on the surface of the planet, we can actually kind of postulate a global time, and I'm going to do that. So I'm going to assume that there is some global time t, and it's the same everywhere at the same time. And on the surface of the Earth, that is fine. We can use atomic clocks for that. If we put atomic clocks in different places on the surface of the Earth, they will stay within very, 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 very close of each other. Okay, so let's just pretend we have like a global time t when we describe algorithms that's using time. We can actually, but you won't be subjected to this to the exam, I promise you that, but we can actually import this assumption into our formal model of what computers were, or what systems were. We call that we had this notion of an interactive agent. We can also make a notion of a timed interactive agent, which is just an interactive agent which has an extra little port here where it can ask what the time is. Whenever it asks what the time is, it goes to one common global interactive agent that's sitting here. There's nothing magic about it. It's just an interactive agent that keeps inside it an integer that we think of as the time. It starts out being 0, and it has a little extra port up here that whenever the environment inputs something there, counts as a tick, it will just increment its time. So the time is like 1, 2, 3, 4, 5, and we don't need to think much about what the units are. It's just some integer time that's progressing. And all the interactive agents in the system can ask the same clock what time it is and then get back what the time is. Okay? So we don't think in the model, we don't think of this here as a clock. We think of it as a model of the physical time. So in fact, algorithm shouldn't use it because no algorithm has access to the physical time. Instead, it can be used to phrase safety property relative to time. So it's used only for modeling purposes. If we want to use time in a protocol, we will model a clock. So we can model a clock, something like this over here. So it will be something which can be influenced by the environment. For example, the environment can put in a drift, say, this clock is 2 seconds behind. And then it has an API down here where the computer can actually read the clock. And then when it reads the clock, what this model here of the clock will do, it will access what is the physical time. And then it will add whatever mistake that we have chosen to model. So if it has been input here on this influence port that this clock is 2 seconds behind, then it will output the current time whenever queried -2. It could also be that the influence is that the time is somewhat random or something else. Okay. So it's something that we try to encapsulate into clocks when we model it, or to talk about when we talk about safety properties. It's nice to have a notion of global time. If you want to say when a message is sent, then it will be delivered within 10 seconds. I need some kind of global time for saying that. Okay. You don't even have to read this in the book. I just wanted to mention that this is how we do it. Later in the course, we'll just talk informally about time and assume that algorithms have access to time and it's the same global time. Okay. Computer clocks. Okay. So there are no time, there's only clocks. So, I mean, it's just about the quality of your clock compared to the quality of some other clock, in particular the atomic clocks that's defining what time it is. So what about the computer clocks? Because there seems to be time in my computer, I can see what time it is. The way that is done in most computers is there's a quartz crystal that is put under tension, put in an electric field, and then you can measure some oscillations on it. And then you count those instead. And we have a good physical model of how often this thing will oscillate compared to how often the cesium-133 atom does it. And then we can use that to measure time instead. This is not nearly as precise. This thing, I mean, a computer clock, if left alone, it will tend to drift around 1 second in 10 days. And it depends on temperature and all kinds of other things. So it's hard to make them precise. This is fine to run the clock on my computer if the purpose is to I mean, have me go to lunch in time every day. I mean, even if it drifts 1 second every 10 days, after 50 years, I'm probably not even 10 minutes late for lunch. However, 1 second is actually a lot if you look at a modern computer. It means that the time on the computer will be drifting around 1,000 instructions per second. Okay? But that I mean, like the time drift the computer has in 1 second, that is, if it's measured with computer instructions, it's around 1,000 instructions. That means if you would want two computers to execute two instructions at the same time somewhere in a system, this drift would be huge. I mean, they would end up being 1,000 instructions away from each other. So you could never use a computer clock to fully synchronize a modern computer system. So there are two ways to deal with that. Don't use time or synchronize clocks very, very finely, and we look at both of them in the course. Another problem, of course, is the time on a computer could have been set wrongly. Someone set it wrongly in the operating system, and then it's just behind, not because the clock is running at the wrong speed, but because it was just set wrongly. In both cases, what we would like to be able to do is then do what we call clock synchronization. So the setting is, I have a server with a precise clock, and I have a client with a bad clock. Now I would like a protocol between the client and the server where the client will learn let's say how much its clock is ahead. This would be what we call the offset. And then what? I mean, why would we like to learn it's ahead? Well, because we want to adjust the clock on the computer. So how would we do that? Let's say I learn that my computer is 2 seconds ahead. Would I just put the clock 2 seconds back? The answer is no. I don't. Let's say I'm a bank and I have inside my system, I have an instruction that every day, 2 seconds past 12, I transfer 1 million to some other bank. Just we need a money flow in that direction. Now, if the time is set back 2 seconds, or just around this time, I will do the transfer, and then I will do it again. So putting the time back on a system is in general a very bad idea. We don't like time travel, and neither do algorithms. So if your clock is ahead, you don't just put it back, you will slow your clock down instead. Unless it's dramatically ahead, years or days, and I'm like really a mistake. But if it drifted a few seconds, you will just slow it down so it will catch up or catch back with the real time. Also, that's much better for avoiding drift in the future. If your clock drifted ahead, it's probably because it's too fast, so it's much better to put the speed of the clock down instead of just putting the clock back. And actually, similarly, we don't like to have time make big leaps forward, because we could jump some time where something significant had to happen in an algorithm. So instead, we just put up the speed a little bit if our clock is behind. Okay? And that also has the advantage that if you're doing clock synchronization many times in a row, whenever you're ahead, you could just slow down a little bit. Okay? And then if that was not enough, then you will also be ahead next time. You could put it down a little bit more. And that means if you make a mistake once, it doesn't dramatically affect the system. So it tends to be a very stable system where your clock will be just around that of the server. And if you start drifting, you will slowly put it back again. If you make a mistake and make it too slow, it will just come back again. So you will never make big mistakes in the system. So that said, let's go back and just focus then on how do we learn the offset. I'm a client, I have a precise server, I want to know how much is my clock ahead. Yeah, okay. I'm going to move myself a little bit. This is basically what I said, but so when we talk about clock drift, right, we talk about it relative to physical time. So we allow ourselves to assume physical time. So if I'm plotting time running to the right and I'm clocking the drift, I'm plotting the drift up here, that's the clock minus time. A clock drift would be how far you're drifting away. Right? And this is what we would like to learn. So it's positive when I'm ahead. Basically, what we would like to do with clock synchronization is synchronize often enough that we keep the clock close to physical time. And then the maximal drift away from it, this is what we sometimes call the max drift of the system. So again, if we have a good model, a good idea of how much our clocks could drift, we can also calculate how much will they drift in some time period. We also have a good idea how long it takes to synchronize them. We know how early to synchronize to stay within some max drift. Again, that is very simple math. So let's just skip that, leave it as an exercise, and then focus on the slightly harder problem of how do we learn how much we are ahead. And I guess all of you can kind of see why it's not trivial, right? I mean, why the trivial algorithm of just asking the server what time it is doesn't work. It's because it takes time for messages to travel in a network, right? And we don't know what that time is typically. So if I ask a server what time is it and I'm told it's 12 o'clock, then it was 12 o'clock when it sent the message, not when I received the message. So I cannot just use that to adjust it. So I would need to know the delay here. Right? So I ask the server what time is it, I get back an S. And then how much I'm ahead, that is my clock, my client clock here, minus the server clock, and then also minus the delay, because it took a little bit of time for the message to come. So I would need to know this delay here, actually, to set my local clock. So, and it's very hard to measure a delay in a network, right? Because the delay in a network, it's the time from when the server sent the message until I received it. And so we cannot just have the server tell at what time it sent it and then subtract my time, because the problem is our clocks might not be synchronized, right? So I don't have a common time, and I have an event that happened at some time up here, and then later I observe it down here. And I would like to know how long did it take for that message to travel. That seems hard, right? And in fact, to some extent, it's also impossible if we don't have any other guarantees than that. Okay, let's look at how we can solve it to some extent. Here's a network time protocol, which is solving this seemingly hard problem under two little bit brave assumptions, but still justifiable. Okay, so the protocol makes the following two assumptions about the network and the time. It says, so during the time it takes to run the following protocol, and it's a simple protocol, it's two messages, ping ping. The clock of the server and the client should not drift very much relative to each other. Okay, so it shouldn't be that the clocks drift 1 hour every second. Then this thing here will be useless. But if it's something like what we talked about before, that it will drift 1 second in a year, something like that, then within the time it takes to send two messages, I mean, the thing will drift milliseconds, or less than milliseconds. And then we will just be able to only synchronize within that little error, that millisecond. That's okay, we're going to live with that. The second assumption, which is even braver, is that we are on a network where we don't know the delay. However, we assume that the delay behaves such that it's approximately the same in both directions. So if I send a message from the client to the server, that would take approximately as long time as it takes from sending it from the server to the client. And again, over small time periods. I mean, it can be that during the day it varies a lot because the traffic on the internet is going up and down, stuff like that. But we assume that in most cases, within like a very short period of time, it takes approximately the same time to send back and forth. Okay? Then we can solve the problem. Maybe you can even think about how to do that yourself. I mean, the first thing that comes to mind, right, is just to measure then the delay, right? And we just send a message up and have it back, measure how long that took, and divide by 2. Doesn't exactly work because in fact, sending is so fast that, I mean, the sending time is comparable, let's say, to the time spent on the server, just doing stuff like receiving the message, preparing a message to send back, saying what time it was when it saw it, and so on. So we need to do a little bit more than that, but it's clear that under this assumption too, right, if computation was instantaneous, I could just ping the server, send it a message, say, send this back, ping, ping. That would be, I mean, the time it takes to send and receive. Assuming that it takes equally long in both directions, I just divide by 2, and then I have the delay, and then I can do what I did before. Right? I just have the server also return me what time it is. And I know the delay, I know my own clock, and then I could do what we just did before, the trivial algorithm. Okay, let's make a drawing. So this is the heart of the network time protocol. So what it will do is, there's a client down here. It sends a message up, and it sends it at T1 and remembers what time it was, T1. Sends it up to the server, which receives this request. This is a time server. Maybe there are millions of clients synchronizing up against it. So it's getting millions of these requests in. So it can't just solve all of them instantaneously. It has a queue of requests, okay? But it might actually take some time to process them. But what it can do is when it receives a message here, it will just write down immediately at what time did I get the message, put it in a queue. And then later, it will process this request. So down here, it's finally ready to reply me. So the server will look at what time it is. Now it's T3, it puts that into the message, and then it sends it. And in fact, it will prepare everything. It prepares the message. It allocates memory for the message in the operating system. It opens a connection and a port to me. It has everything ready, and then it reads the system time, writes it in, and then ships the message off. So we hope that this message gets really when this message was sent, and this was really when it arrived on the server. That is sent back to me, and then I record the time T4 here when I received it. Significantly, the server is sending along T2 and T3 here and telling me what these times are. And then I would like to be able now to compute what is the delay on the network right now. Because T3, right, that's on the clock of the server, and T4 is on the clock of the client. And we don't, I mean, the server could be in a different century. I mean, these clocks have nothing to do with each other. The whole story here is the clock of the server and the client. They're not close to each other. They're running at approximately the same speed, but they might have drifted away from each other. So we can never kind of compare directly time here and time up there. Yet I would like to know this distance here. I would like to know if I took T3 and moved in physical down here and look at what the clock was on the client here, then I would like this thing here minus that thing. That's the delay I would like to know. So what I can do instead is I can say, I mean, I can calculate the total time the protocol took as T4 minus T1, because those are times on the same clock. That's a meaningful, that gives a meaningful period of time. And then I can subtract from that kind of the time that the message was not in transit. That is T3 minus T2, right? Again, those are on the same clock, and they were sent down to the client, so the client can subtract them. And then we subtract that from the total time. And then we have the time in which the message was in transit. But significantly here, to get the current network delay, we'll have to divide, of course, this by 2, because there's 2 times sending. And then under assumptions 1 and 2, this is a reasonable estimate of the network delay. And then I know how much I was ahead. That's T1 minus that thing here, which is T2, but with the delay. Okay. And then that would give me how much I'm ahead, and then we're done. And then the network time protocol is actually doing a little bit more. So what it's doing is, it's not doing this once, it's doing it several times in a row. I think 8. by default. And then it's using the smallest delay. Okay, so it's just doing it many times and then using the smallest delay. The reason for that is that, the delay on the network, it will undergo some kind of stochastic influence. Sometimes it's larger, sometimes it's smaller. And also sometimes there will be a burst error. So like a message gets sent and then it gets through because some server was doing something. Some server was garbage collecting on the way. So it got a message in that it had to send on. That's how the internet works, why messages gets relayed. Maybe there's a server in the middle here that did some hiccup and the message got delayed and then it moved on again. When that happens, it will typically happen to just one message. And then this assumption we have fails. This assumption that sending a message from the client to the server and back again, that it takes the same time, it would not be true because ping, and then it gets through. And that means our algorithm at that point would give a bad estimate because one of the assumptions are false. However, when stuff happens in a system, it's typically that messages gets delayed. It's rare that we see networks which accidentally become faster. Right? So when bad stuff happens, the network gets slower. Therefore, we can just say, okay, when the delay is minimal, the network was very fast, so probably there were no mistakes. So that is the run where it's most likely to be true that it took the same time to send back and forth. And therefore, we go for that number. We're kind of just looking at the estimate and using that as a feeler whether the network was in good conditions when we did that one. And then if sometimes we're even more unlucky, and this is also a bad estimate, remember that we're only adjusting the speed of our clock a little bit. So if we just do this often enough, it won't completely screw up the system. If we get a bad estimate now, maybe in the next 3 are good, and then we'll get back again to a good clock speed. So that's the rationale behind the network time protocol. That's assuming that you have access to a server to synchronize up against. There's also that you can talk to and get a message back from. There's also the global positioning system, which I would like to address a little bit, which is different than in the sense that it only has one-way communication. So it's what happens here is you took the server from before, and then you just put it in a satellite. So you take an atomic clock and you put it in a satellite. And then when you're walking around, in particular outside, your watch, I have a watch here that I use for running, it can talk to the satellite and ask what time it is. The problem is we can't use the network time protocol now because we don't know how far the satellite is away, and we can't send it a message. We can only receive from the satellite. So what the satellite will do is, it's circling around the planet. So it will remember its 3 spatial positions, X, Y, and Z. And then it will also have an atomic clock, so it know exactly what time it is. So it will just constantly beep out these positions. It will tell us where am I and what time is it. And what time is it? But the problem is it takes time for this signal to travel, as we discussed before, right? And I now can't get an estimate of how long it took because I can't send the signal and get it back again. The satellite doesn't want to talk to everybody, and my running watch don't want to beam signals to a satellite. It would be out of power in 5 minutes. Right? So it's a passive system where you only get the signal beamed down. So you get it's 12 o'clock, but you don't know where the satellite was. Was it here? Was it far away? So you have no idea what the time is when you receive that signal. Therefore, and because there are 4 unknowns basically here, what you need is to not hear from 1 satellite, but to hear from 4 satellites. So you hear from 4 different satellites. Where were they when they sent the signal, and what time was it? The positions will be different, the times will be different, and then you just solve the equations. But the math you have by now, you should be able to sit down and do that. It's trigonometry in 4 dimensions. So let's just try just to illustrate that it's possible to solve these equations, to look at it in 2 dimensions. Okay. one spatial dimension and one time dimension. So we're living on a line. So we are living on a line. We can move back and forth on a line, and then there's also time. Time is also traveling. So let's say I then hear a signal from two satellites. One of them tells me I'm at position 4 and the time is 0. And another one is telling me I'm at position 12 on the line and my time is 4. Then the question is, where are we on the line and what time is it? I mean, the time should be after 4, right? We received the signal that's 4, but what time is it and where are we? I mean, are we in between 4 and 12? Are we to the right of 12 or to the left of it? So think about it for a second, how you would solve that thing. Where are you and what time is it? So this is the best way to think about it, at least for me. We do these time cones. I'm gonna draw the spatial dimension in this direction. Here the unit is how far light travels in a second, also called c. And up here is time in seconds, okay? So that means, and then anything can be put in here, right? If I put something, let's say here, it means it's at position 4 and its time is 2 o'clock. So we just turn a timely world into a static two-dimensional world, right? Now, a signal sent by the satellite is traveling at the speed of light, approximately. So these signals, they will travel then as 45-degree things here, right? Because they will travel up a second and right is how far something travels in a second. So this is a signal beamed out by a satellite. So if I had a satellite down here at position 4 at time 0, it would send out 4,0. I'm at 4, the time is 0. And that beam is that inverted pyramid here. The other thing was, we also heard some satellites saying, I'm at position 12 and the time is 4. So it was here, and then it sent out the signal. The only places where you can receive these signals is on these lines, right? So if you receive this signal here and you're at position 6, you will receive it at time 2. Right? So you don't know where the satellites are, but you know that when you receive their signals, you're on these cones here. So you can go and plot the time you received, plot these the pyramids. And then you just take two signals that you received at the same time. And then now you know you are on a point where these things intersect. So you know you are here. So you are at position 10 and the time is 6. Okay. And until you have 4 signals, you have a full freedom. So there's something you don't know. You don't know what time it is, or you don't know where you are. But the second you have 4 signals in 3 spatial dimensions, you know exactly where you are and what time it is. So that's how you use the GPS system to learn what time it is. Okay. Yeah, position 6 and the time is position 10 and the time is 6.